Welcome back, everyone. In this video, I'll be continuing the section on indeterminate forms or L'Hopital's rule. Now, number 4 here, it says we want to evaluate the limit as x goes to infinity of 5x squared minus the natural log of x. And it's not a fraction, but if it is an indeterminate form, then we're going to have to turn it into one. Well, we still want to make sure that it actually is an indeterminate form. So what happens if we plug in infinity? This thing isn't a polynomial, so you can't say the answer is plus or minus infinity. It is just pretty much something minus something else. And unfortunately, it's not a polynomial, but what we can go ahead and do is plug in infinity or take the limit of each part. Now the limit of x squared as x goes to infinity is infinity, and then times it by 5 is still infinity. So the first part's infinity, and then minus, and the limit as x goes to infinity of the natural log is also infinity. And this is the subtraction or difference indeterminate form. It's the only one where there's a minus. There are no pluses, unless if it's like negative infinity plus infinity, because that's just the same thing rearranged. But the only one with a minus is infinity minus infinity. This is, though, an indeterminate form. And the thing about this is we have to make sure we rearrange it, we do something to it to make it into 0 over 0 or infinity over infinity. And once again, plus or minus doesn't matter on the infinities, as we know. Now, in order to do this, there's many ways. And probably the way that works the best is factoring out something. Now, the thing is, when you factor out something, because it's not a polynomial, and in general, if we had a polynomial, we could narrow down the answers to 1 or up to, and then just see which one's correct. When it's not a polynomial, when you factor something out, it's going to force a fraction. And what I like to do in this sort of setup is factor out powers of x. I don't want to factor out the natural log of x because it's just going to make it a little messier. So what I want to do is factor out x squared. You can factor out the 5x squared if you want, but I want to factor out x squared. And in general, you can factor out the largest power of x. Now, if you have like e to the x minus ln of x, then you could factor out the e to the x. In general, ln of x is the last thing I like to factor out because it's just messier to deal with, and you can just let it be. For lack of a better term. All right, so we're not going to actually do any L'Hopital's rule yet because we can't. We have to rearrange it. And when we factor out the x squared, the 5x squared just becomes 5. Now, because the ln of x has nothing to do with x squared, we have ln of x. And because we factored out something that's not really there, to make up for it, we have to divide by the x squared. And what's going to happen is this is exactly going to help us because this is where our fraction is going to come in. Right. Now, the nice thing about limits we know is that limits work over products, meaning we can do the limit of x squared times the limit of this. And that's another big reason why we do it like this. So the limit as x goes to infinity of x squared times the limit as x goes to infinity of 5 minus the natural log of x over x squared. All right, so let's go ahead and do that. I'm going to put these in parentheses individually because we know we're doing the limit of each part. Well, now the limit of x squared as x goes to infinity is infinity times the limit as x goes to infinity. Actually, let me go ahead and not write that because we're going to evaluate it. We have parentheses 5 minus, and the limit as x goes to infinity. Well, in this fraction here, we get infinity on the top and infinity on the bottom. So what's happening here? We have some other stuff. And the other ones, we just had infinity over infinity. Well, the thing is, what the laws of limits say is that we don't have to redo the entire limit at all. We just need to focus on this part. All right, so the part that gave us infinity over infinity was this. And we need to do L'Hopital's rule on this part. Now, nothing else here is giving us a problem as far as indeterminate form. We have infinity, that's just by itself, that's fine. And then we have a 5. So what we're going to do is go ahead and write it like this. I'm going to take where I was at here, but because the infinity and the 5 are fine, I'm going to write it from this spot. This equals the limit as x goes to infinity of x squared is infinity times the limit as x goes to infinity of 5 is just 5 minus the limit as x goes to infinity of the part that gave us infinity over infinity, which is ln of x over x squared. So when we did the limit of each part before, this is exactly what gave us infinity over infinity, but we just have to backtrack and do L'Hopital's rule on that part. The rest can stay exactly as it is. All right, so we got infinity times 5 minus, and we're going to do L'Hopital's rule. Now we're only doing it on this part, but that's the only place we have a limit left, so that's fine. And when we do L'Hopital's rule, we do the limit as x goes to infinity. The derivative of natural log of x is 1 over x divided by the derivative of x squared, which is 2x. And once again, it's just this part of the limit. So whenever we do L'Hopital's rule, it doesn't have to be through the entire thing. Most of the time it is using the entire thing, but this method, when you factor out something, is going to give you always some multiplication times and then whatever's left, and hopefully whatever's left is what you do L'Hopital's rule on. All right, so let's go ahead. We've done our L'Hopital's rule. We're going to simplify. I'm going to leave the infinity times and then the 5 because those are already done, minus the limit as x goes to infinity. And we've dealt with this before a few times. 1 over x, you have the 1 on the top, and then the x comes to the bottom, so it's over 2x squared. And now when we do this, as x goes to infinity, we have infinity times parentheses 5 minus, and what's the limit as x goes to infinity of this? Well, the positive power of x is on the bottom. So when we do the limit, the top is 1, it just stays there, and the limit of the bottom is infinity because it's the limit as x goes to infinity of x squared is infinity, and it multiplies by 2, so that's infinity. We were reminded in a previous problem that a number over infinity is really 0, so this is infinity times 5 minus 0, and this is just 5. Infinity, or a very large number, times 5 is infinity, so that is our answer. Remember, that is not an indeterminate form, it's just infinity. Now there are other ways to deal with this difference one, infinity minus infinity, but I think this is the most straightforward way. The other way involves doing things with exponents and applying exponent rules, and what happens when you do all that stuff is that the derivatives get really messy and you actually did something that requires you to undo it at the end, so the answer you get at the end, you're not going to be quite at the answer. It's going to be a necessary step when we do a different form, but for this form, this is the easiest way. So I just want to go up and outline exactly what we did here for the difference one. So this example here, what did we do? Well, really what we did is we factored out something. Kind of mentioned that just the general rule of thumb is I factor out powers of x, then I would factor out e to the x, and the last thing I would want to factor out is a natural log of x. But we factored out something. We can say C number 4, what we did, and that's really how you deal with all of these. All right, so number 5 here, this is kind of a special problem in the sense of I think it's a little complicated, but it's not terribly complicated. It's pretty similar to number 3 above. So this is the limit as x goes to pi over 2 from the right, so it's already a one-sided limit of cosine of x over 1 minus sine of x. Well, we know even if we have a one-sided limit, we just go ahead and plug in the number. So we get cosine of pi over 2 over 1 minus sine of pi over 2. And this is 0. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So 1 minus that is also 0. And it's already in L'Hopital's rule form. So we're going to use L'Hopital's rule immediately. Now, like I mentioned, oops, it's not to infinity, out of habit because we do this so much with L'Hopital's rule. But like I mentioned before, when you do a one-sided limit, L'Hopital's rule, everything is the same. So we've got our original cosine of x over 1 minus sine of x, and we do the limit as x goes to infinity, or sorry, I keep wanting to do infinity, but it's pi over 2 from the right. And then L'Hopital's rule tells us do the derivatives. We do the derivative of cosine of x, which is negative sine of x. And we do the derivative of 1 minus sine of x, which is negative cosine of x. And now you can simplify this by just getting rid of the negatives. What I would advise is not write this as what sine over cosine is, which is tangent, because having a fraction is very vital. If we have to do L'Hopital's rule again, then we know that writing this as tangent is not going to be very helpful. All right, so let's go ahead and plug it in. We get sine of pi over 2 over cosine of pi over 2. We applied L'Hopital's rule, we simplified. And sine of pi over 2, we just dealt with both these. This is 1 and this is 0, cosine of pi over 2. Now this is pretty much the same thing as number 3. And at this point is because this is a number over 0 is either plus or minus infinity. Because it's a one-sided limit, we're pretty much guaranteed it's not going to be D and E, it's just going to be one of these, because we don't have to come at it from both sides. Well, how are we going to do it? We're going to do it exactly the way we did it before. We take our original function. We want to plug in number slightly larger than pi over 2, because we want to come at pi over 2 from the right. So an easy way to do that is just take pi over 2 and add 0.001. And that's what we can plug in. Now it's going to look messy when we do it because we're plugging in a pi over 2 plus something. But if you go ahead and plug this in, what's going to happen is it'll all work out for us. All right, so you have to make sure you plug in pi over 2. If you plug in like 3.14 and then you add this, you might actually be to the left of it. So we're going to have to make sure we plug in exactly something like this. We got cosine. Remember to plug it into the original we saw at the end of the last video, why you should do that. We have cosine of pi over 2 plus 0.001 over 1 minus sine of pi over 2 plus 0.001. And let's go ahead and see. We only need to notice one thing, whether that's positive or negative. We should be close enough to pi over 2 to where it doesn't matter. And we are. But if you don't have a number where you can confidently say you think it's positive or negative infinity, just add another 0 and do 0.0001. All right, so let's see what we get. We get cosine of pi over 2 plus 0.001 divided by, parentheses because I have a minus in the division, 1 minus sine of pi over 2 plus 0.001. And we kind of saw the number there, but we can press enter and make sure we're doing it. And we did type it in correctly. It's basically negative 2000. That should probably convince you that this is negative infinity. All right, so this number is negative 2000-ish, which is telling us the limit is going to be negative infinity. Now, once again, you can always confirm these because it's a little unsatisfactory to plug in a number just to get a limit, but it's really what we have to do to distinguish between positive or negative infinity. So we can go ahead and just do y equals cosine of x divided by 1 minus sine of x. And then if I go ahead and hit this and little toolbar and change the step size on x to pi over 2, then this is pi over 2. As we come towards x equals pi over 2 from the right, it goes down to negative infinity. So we can see that does work out for us. So that's just another one that's sort of like the first three, but slightly different. So not a new technique here. So I'd actually think this is a good place to stop. We got 2 problems left. We're going to have one for the product, 0 times infinity, and one for the exponent. And the exponent form has 3 different possibilities, but it's not a big deal. We're all going to approach them the same way. So I'll see you in the next video.